In this video, I will present you my paper called State Complexity of Chromatic Memory in Infinite Duration Games. And there I studied the following problem, which I will first describe to you via the following example. So we have a directed graph here. Some of its edges are colored into red and some are into blue. And our goal is to find an infinite path which starts in the leftmost node here and which maximizes the number of consecutive blue edges. More precisely, if I have an infinite path, then I can consider the maximal natural number k, such that somewhere in this infinite path there are k consecutive blue edges. And so our task is to maximize this parameter. Let's see what we can do here. Okay, until we reached the square node, we have no choice but to go to the right. But when we are in a square node, we can, let's say, also go to the right, and then we reach a node with the red loop and no blue edges afterwards. So you see then there will be 3 consecutive blue edges. Okay, but we can also go to the cycle from the square node, and if we just then stay forever on this cycle, then we will have maximum 4 consecutive blue edges, right? Because after any quadruple of blue edges, we will have 2 red edges. So now we can see that the optimal way is to first go to the cycle from the square, and then when we return to the square, we have to go to the right, and then we will have 5 consecutive blue edges. Now, what's the problem? I'm interested in the amount of memory I need to realize this optimal infinite path. And in fact, I'm interested in 2 kinds of memory. One is general memory, and the other one is chromatic memory. It's just some special case of general memory. And but let's just see what we can do just with general memory here. Okay, well, the idea is that I have to do different things at the square node at different moments. More precisely, when I'm there for the first time, I have to go to the cycle, and when I'm there for the second time, I have to go to the right. And for that, I basically need just 2 states of memory. I just need to remember whether I have already been to the square node, right? And if I haven't, then I go to the cycle, and if I had, I go to the right. Formally, you can realize this via a finite automata. So this will be how we define general memory, is through a finite automata whose input alphabet is the set of edges, and the number of states in this automata will be the number of states in your memory. And in this particular case, so how we can do this? So we just need 2 states, whether or not we have already been to the square node, and the initial state is, of course, that we haven't. And when, and so the input alphabet of this finite automata is the set of edges of our graph. And when it receives an edge which starts in the square node, which indicates that we have already been there, so our automata, which realizes our general memory, transmits from the state that we haven't been to the square node to the state that we have been there. Okay? And so this finite automata with 2 states realizes our optimal infinite path. Okay, that's general memory. And what is the chromatic memory? The chromatic memory is that it is only allowed to observe colors of the edges. In other words, a finite automata realizing a chromatic memory, its input alphabet is not the set of edges of our arena, of our graph, but the set of colors. And when it receives an edge, it just reads its color. Okay? And the previous solution doesn't work because the chromatic finite automata cannot distinguish between an edge which starts in the square node from other edges, right? Because it can distinguish only edges only by their colors. So what we can do here with chromatic memory? So, okay, when we first reach the square node, the sequence of colors was red, red, blue, blue. Then we obviously have to go to the cycle, and then when we return to the square node, the sequence of colors will be red, red, blue, blue, red, red, blue, blue, blue. And we have to do at this moment something different. We have to go to the right than what we did after red, red, blue, blue. So basically, our automata has to come into different states on the following two words. One is RRBB, and the other one is RRBB, RRBBBBB. Okay, and it can be shown that there is no two-state automata which does that. No two-state automata of the alphabet of R and B, with the letters R and B, which does that. Well, okay, it can be verified by computer search, but let's just see that there is nothing obvious here that obviously works. Okay, for example, we can track the length of a word modulo 2, but one word is of length 4 and the other of length 10, so it doesn't work. We can also track the number of R's modulo 2 or the number of B's modulo 2, but okay, they have the same parities in these two words. Or we can, I don't know, let's say we can track the last letter of the word, but they have the same last letters. And okay, that's just, that's, of course, we need computer search to formally show it. But what's the conclusion here is that in this specific task, we need two states of general memory and at least 3 states of chromatic memory. More generally, I'm interested in the following problem. So we consider H-colored graphs. But the difference from previous example is that some nodes might be controlled by an adversary. It means that in these nodes, adversary decides where to go next, not we. So basically, we play a game against an adversary. And this game proceeds for infinitely many turns. So this gives us an infinite path in our graph. And we look at the sequence of colors along this infinite path. And our goals are specified by a winning condition W, which is just some set of infinite sequences of colors. And our goal is to ensure that the infinite sequence of colors produced by play belongs to W. So we need a strategy, we will call it a winning strategy, which ensures that no matter how adversary counterplays against this strategy, the resulting infinite sequence of colors belongs to W. And again, I'm interested in the amount of memory that I need to realize this winning strategy. And in fact, in two kinds of memory, general memory and chromatic memory. And there are actually two settings. One is non-uniform. In the non-uniform setting, we are given a game graph G and the winning condition W. And then general memory of G and W is the minimal number Q, such that there exists a strategy with Q states of general memory, which is winning for W in the game graph G. Okay, and again, what does it mean? General memory. It means that it just can be realized by a finite automata with Q states, and its input alphabet is the set of edges of G. So what basically happens is that we carry this finite automata with ourselves during the game. Each time the next edge is produced, we feed this edge into our automata. And at each point, we know the current state of our automata. So whenever we have to make a move from some node, we know this node, and we know our current state, the current state of our automata. And this is all that we know. And given this information, we have to decide our next move. And okay, so general memory of GW might be infinite. For example, if there is no winning strategy. And it can also be infinite if there is some winning strategy, but it cannot be realized with finitely many states. But in any case, we can also define the same thing, but for chromatic strategies. So chromatic memory of GW is the same thing, but we only take into account strategies that are realized by finite automata that only read colors of edges. And we are interested in the relationship between these two quantities, general memory of GW and chromatic memory of GW. Of course, since chromatic strategy is basically a special case of general strategies because they are just, we can just consider a finite automata whose input alphabet is the set of edges, but it only reads the colors of these edges. So general memory of GW is at most chromatic memory of GW always, but what else can we say? Let's say, can we say that if general memory of GW is finite, is it true that chromatic memory of GW is also finite? And the other setting, which is also of our interest, is the uniform setting. In this setting, we define general memory of W. How? So we consider all game graphs G where there is some winning strategy. And then we consider the maximal overall size G of general memory of G and W. So basically, general memory of W is the minimal Q such that whenever you have some winning strategy with respect to W in some game graph, you also have a winning strategy with at most Q states of general memory, which is winning also. And then we also define the same thing in the chromatic setting. So chromatic memory of W, you consider all game graphs G where you have some winning strategy with respect to W, and then you take the maximal of the chromatic memory that you need to win in these game graphs. Again, both these quantities can be infinite, but we are interested in their relationship when they are, say, both finite. We can, of course, again say that general memory of W is at most chromatic memory of W for any W. But what can we say? But what else can we say? That's the questions that we study in this paper. So memory requirements for this kind of games on graphs has been studied for decades, but this chromatic memory really became a thing only very recently. So I will show you why is that. First, it is interesting for so-called Muller conditions. A winning condition W is Muller if whether or not an infinite sequence of colors belongs to this condition is determined by the set of, one might say, limit points of this sequence. So by the set of colors that occur infinitely often in this sequence. For example, the following condition is Muller. Let's say you win if exactly two colors appear infinitely often in your sequence. And this is classical that chromatic memory of any Muller condition W is finite. And this follows from some well-known result. First, you need a deterministic parity automata for any Muller language. In fact, it is known that such thing exists for every omega regular language. And then you also need positional determinacy of parity games. But still, okay, so we have this fact. The question is, okay, so what is the exact, how to determine this chromatic memory of W and also general memory of W? And there is a series of results of Casares, Colcombet, and Letinin. So they have shown the following. They basically have shown that chromatic memory and general memory, in case of Muller conditions, has an automata characterization. more precisely, chromatic memory of W, which equals just the minimal size of a deterministic Rabin automata recognizing W. Okay. And general memory of W equals the minimal size of a so-called good for games Rabin automata recognizing W. Okay, well, good for games automata, maybe it's not so well known notion, but it became really popular in recent years. So basically, this is a non-deterministic automata with Rabin acceptance conditions, and in a sense, it can be determinized on any specific infinite path. Okay, but in any case, it's interesting that chromatic memory and general memory, their relationship in this case corresponds between the relationship of two interesting kinds of automata over infinite words. And it also allows us to obtain a separation between chromatic memory and general memory. Namely, there was a conjecture of Kopczynski from 2006 that chromatic memory always equals of omega, always equals general memory of omega. For any omega, or you can state it for Muller conditions, it was not known, but Casares refuted this conjecture using this example, using this theorem, this automata characterization, and using this example that we have seen on the previous slide. So we can consider Muller conditions where you win if there are exactly two colors that appear infinitely often in your sequence of colors. And it turns out that general memory of this winning of this Muller condition is 2, and whatever is the number of colors. But chromatic memory of this Muller condition equals the number of colors. So it can be strictly larger than general memory. And another recent result that raised my interest in chromatic memory strategies is the following theorem of Bouyer et al. So they consider a class of winning conditions W such that the chromatic memory of W and its complement is finite. So basically, we're interested in cases when we can play with just finitely many states of chromatic memory whenever we have some winning strategy. And the same holds for our adversary. And they obtain the following result, which is sometimes called 1-to-2 player lifting. So they show that if winning condition W is such that its chromatic memory and the chromatic memory of its complement is finite for graphs without adversary, so basically for one-player game graphs, then it also holds for game graphs with adversary. So then it's also finite for W and for complement on W for all graphs. And it gives, so basically, and they call this class of winning conditions arena-independent finite memory determined. And basically, this result gives us some kind of characterization of this class, because we basically can reduce a game theoretic reasoning, so a reasoning about graphs with adversary, to reasoning about graphs without adversaries, just to solely graph theoretic reasoning. And obviously, now it's interesting to understand whether we can obtain something similar for the class of omega, for which both general memory of omega and of its complement is finite. Of course, this class can only be wider, right? Because if chromatic memory is finite for both V and its complement, W and its complement, then the same holds for general memory. But in fact, it's unknown whether this class is wider. So it is unknown whether it holds that if general memory of omega is finite, whether it is always true that chromatic memory is also finite. But it is known that it's not always true if the number of colors is infinite. In fact, due to the previous example of Casares. because in the previous example of Casares, the chromatic memory was equal to the number of colors, and if it's infinite, then actually chromatic memory will be infinite. But still, this question on the bottom is open for in case when the number of colors is finite. So maybe it holds that if general memory of W is some Q, then chromatic memory of W is bounded by some expression which involves Q and the number of colors, let's say. So it's a very interesting open question. Okay, now I would like to formulate our results. So our results are only for the non-uniform regime, unfortunately, but in this regime, they are quite tight. So first we have obtained the following upper bound. For any winning condition omega and for any G, game graph G with n nodes, it holds that chromatic memory of G and W is at most general memory of G and W plus 1, and all this to the n. And this is an exponential improvement over the following bound by Leroux, who among other things have shown that chromatic memory of G and W is always at most 2 to the general memory of G and W times n squared plus 1. What is important here is that in our upper bound, general memory is not in the exponent. Why is it important? Well, I think it's important because if you measure, so here we measure memory in the number of states, like in finite automata. But we can also measure it in bits, and then we basically just have to take the log of the number of states, and then our upper bound states that chromatic memory is at most n times more costly than general memory if you measure it in bits and if n is the number of nodes. Whereas the bound of Leroux, chromatic memory measured in bits, it states that it's at most exponential in the general memory measured in bits. And this basically means if you consider, like, if you allow yourself polynomially many bits of memory for games graphs in n nodes, then basically chromatic and general memory is the same thing. But of course, it might be different in other regimes. And okay, and there is a lower bound that shows that our upper bound is essentially tight, namely, it holds that for any n in Q, there exists a winning condition W and the game graph G with n nodes such that general memory is small of G and W. It's just Q, but chromatic memory is large, more or less the same quantity as in the upper bound. Well, not quite, but it's Q to the n minus 3. And the upper bound gives you Q plus 1 to the n. But essentially, this is tight. And I just want to stress that none of these results, unfortunately, give something for the uniform regime. The upper bound depends on the number of nodes. And in the uniform regime, we are interested in the amount of memory which is sufficient for all graphs. So it cannot depend on m. And the lower bound for any n in Q, we construct more or less a specific winning condition which works for a specific game graph. And unfortunately, it's not clear how to derive here any lower bound on the uniform memory requirements of some winning condition. In the final part of this video, I would like to show some overviews of the proofs. And I would like to start with the lower bound because it has a nice connection to so-called self-verifying automata. So what is it? Self-verifying automata is a non-deterministic finite automata, and its set of states is partitioned into three kinds of states: neutral states, accepting states, and rejecting states. And finally, the most important requirement is that for any input word, either there exists a run of our automaton on this input word, which accepts it, so which leads to the accepting state, or there exists a run of our automaton on this input word, which leads to the rejecting state, and most importantly, that exactly one of these two statements should hold. Not two, not zero, but exactly one. And then if we have a self-verifying automaton, then we can assign to it a language recognized by it by just taking the set of all input words for which there exists a run which leads to an accepting state. And so this notion lies somewhere in between deterministic finite automata and non-deterministic finite automata. Because, well, not all non-deterministic finite automata are self-verifying. Because for languages, for words that are accepted by non-deterministic finite automata, the only requirement is that there exists some run, some accepting run. But there may be as well some rejecting runs on these words that are accepted by non-deterministic finite automata. And we have a requirement that every input word which is accepted, there has to be no rejecting run on it, and vice versa. And as for deterministic finite automata, well, for every input word, there exists exactly one run over this input word. And so it's easy to see that any deterministic finite automata is self-verifying. And so one may ask, what is the difference in state complexity of recognizing languages by deterministic finite automata and self-verifying finite automata? And Geraskova and Pigicini have obtained an optimal separation. So for any n, they constructed a language which is recognized by some n state self-verifying automata, but which cannot be recognized by a deterministic finite automata with less than 3 to the n over 3 state. So there is an exponential separation, and they also show that this is optimal for every language. And why it is interesting for us? Because first of all, we can directly, without looking into the proof of this theorem of Geraskova and Pigicini, derive a weak version of our lower bound. Namely, we can show that for any n, well, q here, there shouldn't be no q, but for any n, there exists a winning condition w and a game graph G with n+1 node, such that general memory of G in omega is 2, and chromatic memory of G in omega is at least 3 to the n over 3. This is a weak version because our strong version, if Q is 2, it gives us chromatic memory 2 to the n up to some constant. And in our weak version that can be derived directly from Geraskova and Pigicini, we have 3 to the n over 3, and it's smaller than 2 to the n. But still, it is already exponential. And but in our strong lower bound, we have a better bound for 2, and we also have a bound for every possible q. But And in fact, to derive a strong lower bound, it is not just sufficient to use this theorem in Zhiraskova and Pidgezzini as a black box, but we actually take their construction and slightly adapt it to our setting and obtain an optimal separation between general and chromatic memory. Okay, so now I want to show this derivation from the theorem of Zhiraskova and Pidgezzini of a weak version of our lower bound. So we are given some n-state self-verifying automata A with the property that any deterministic finite automata which recognizes its language has at least 3 to the n over 3 states. And we want to what we want to get from this is a game graph G with n+1 node and winning condition W such that general memory of G and W is 2 and chromatic memory of G and W is at least 3 to the n over 3. So let's start with the construction of G. So first we consider the transition graph of A. So its nodes are states of A and edges correspond to possible transitions of A. So we want this graph to be edge colored, and well, each transition has an input letter which is assigned to this transition. And so we just consider input letters of A as colors, okay? And we also assume that all nodes of this transition graph are controlled by the adversary, and there is only one node which is controlled by us. It is to the right of the transition graph. And what edges do we have with this node to the right? So first of all, in the transition graph, there are some states, and some of them are accepting and rejecting, and the rest are neutral. And we assume that every accepting state has an edge which is colored in black and goes to the node which is controlled by us, and similarly for all the rejected states. So these nodes, these edges are black, and we assume that black is not the input letter of A. So it's a distinct color from the colors that are inside of the transition graph. And our node has one green loop and one red loop. Okay, so that's it. So this is a construction of G. Now let us define W. But first, let's see what can happen in the game. So first, adversary controls the transition graph. So in principle, it can stay there forever. So and then the sequence of colors will consist entirely of input letters of A. And we assume that this is winning for us. So the winning condition is such that any infinite sequence which consists entirely of input letters of A is winning for us. So if adversary wants to win, it has to at some point has to leave the transition graph of A, and then he can only use some black edge for it, which goes to the node controlled by us. So let's see what will happen in this situation. So we will have some word of input letters of A, then we will have a black edge, and then we will have to use one of the two loops. One is green and the other is red. So, and the winning condition is follows. If we first have, before the black edge, we have a word which belongs to the language recognized by A, then there must be a green loop, green edge. And if before the black edge we have some word which consists of the input letters of A, but doesn't belong to the language recognized by A, then we have to use the red edge. Okay, so, and then we have to argue that we can win using two states of general memory, but we cannot win using less than 3 to the n over 3 states of chromatic memory. So let's start with general memory. So what we understand, so our automata is self-verifying. So all the words
such that adversary on which adversary can come to an accepting states are from the language, and all words from the language has some path to an accepting state. And the similar thing holds for rejecting states and for the complement of the language recognized by A. This means so we can just use the following strategy. If we come to the circle node from an accepting state, then we use the green loop, and if we come from a rejecting state, we use the red loop. And to realize this, we just need to remember whether the last node was accepting. If it was, then we use the green edge, and otherwise we use the red edge. Okay, but that's general memory, because we don't only remember colors. We in fact don't care about the colors. We just care about the last node, whether it was accepting or not. And why then we cannot win with less than 3 to the n of 3 states of chromatic memory? Because let's say we have a winning strategy that uses chromatic memory. Then this chromatic memory is some deterministic finite automata with a set of colors. And it can be converted into a deterministic finite automata recognizing the language of A. Why is that? Well, because basically it has to do different things after we had a word from the language and the black edge, and after we had a word from the complement of the language and then the black edge. So it means, since we can realize any word from the language and from its complement, it means that for any pair, it cannot be, there is no two words such that one is from the language and the other is not, such that our memory comes into the same state on these two words. And this it means that we can use our memory as a deterministic finite automata that recognizes our language. And finally, I wanted to give a proof sketch of the upper bound. So just to remind you, we are proving that for any winning condition W and any graph G with n nodes, we have that chromatic memory of this is at most general memory plus 1 to the n, where n is the number of nodes once again, right? And the plan is to convert any strategy S1 with Q states of general memory into another strategy with Q plus 1 to the n states of chromatic memory, such that call of S2 is a subset of call of S1. What is call of some strategy? It's just the set of all infinite sequences of colors that can be obtained in a play with this strategy. So why is this all sufficient for our theorem? Well, in the theorem we have to show if there is a winning strategy with Q states of general memory with respect to V, then there is a chromatic strategy with Q plus 1 to the n states of chromatic memory, which is winning for W also, right? And if we have this property that call of S2 is the subset of call of S1, then this all holds automatically. So if S is winning for any W, then so is S2. Because what does it mean that S1 is winning for W? It just means that call of S1 is the subset of W. And if call of S2 is the subset of call of S1, then call of S2 is the subset of W. Okay. Now, how we achieve this? And the idea is the following. Okay, we have to, in a sense, we have to simulate S1. So if S2 finds itself in some node, then the obvious thing to do is to do something that S1 would do in the similar situation. Okay, what I mean by that? Let's say you are in a node U. So let's say we are talking about a node U. To know what
what S1 would do, we have to know some state of S1, right? Because the behavior of S1 is determined by a node from which it has to make a move and by a state, by a state of its memory. But this state should represent some similar situation. And we basically are interested only in the sequences of colors. So if for a node U, we would like to know some state of memory of S1 such that there is some play with S1 which brings its memory into the state in question. And of course, it should come to U, and it has to have the same sequence of colors as in our current play with S2 that we are currently playing. But ideally, we would like to know such a state for every node U. But we will know this only for some of the nodes. Well, in fact, in the beginning, we will only know this for the initial node. And the corresponding state for the initial node will be just the initial state of the memory of S1. But in future, we will assign some states to some other nodes. But for the rest of the nodes, we will just maintain some labels that we don't know. There is no sufficient information for these nodes. So basically, each node can be assigned to a state of S1, and there are Q such states, or it can be assigned to a label that we don't know. So S2 will have Q plus 1 to the n states, but it will be chromatic. But we will talk about that a bit later. But one more very important requirement is that when we play using S2, there is always some actual current node from which we have to make a move. And we have to maintain that there is always something assigned to this node, something non-trivial, some state of S1, because we have to do something in this node, right? Okay. Then one question is the following. Let's say we have all of this. Why is this sufficient to prove the theorem? So why we will have that call of S2 is the subset of call of S1? Well, that's easy, in fact, because we have this inclusion, well, an analog of this inclusion for finite plays, because if you have a finite play with S2, then, you just look in what will be the state of S2 after this finite play, then you know that some state of S1 will be assigned to the endpoint of this play. Then and then you use the property that if you have something assigned to this, then there is a play with S1 that has the same sequence of colors, right? And then you just extend this property to the Koenig's lemma, by the Koenig's lemma to infinite play. Because if you have infinite play with S2, you know that for any finite prefix of this play, there is some play with S1 which has the same sequence of colors, and then you just employ the Koenig's lemma. And finally, we also have to show somehow that we can achieve all of this. I will not go into too much detail here, but the idea is the following. Okay, let's say you receive the color C. Your memory should be chromatic, so some H is played in the game, and the memory only sees the color of this H. You know that this is some color C, but this can be any C colored H in the graph, in principle. Okay, but what is our current knowledge? Our current knowledge that before we had this color C, we had some states of S1 assigned to some nodes of our graph. And for these nodes, this means that there existed some place with S1 that
come to these nodes and bring the memory of S1 into the corresponding assigned state. And they also displays, which is very important, they also have the same sequence of colors that we had before we received the new color. And now we have to extend all of this by some C-colored edge. And we just look in all ways that is consistent with S1, in which it can be done. Well, let's say we consider some node which is controlled by us, and for which, before we received the new color, we know we had some state assigned to it. And then, okay, we know that what would S1 do in this state from this node. And if it will go by some C-colored edge, then, oh, that's great for us, because we know what will be the state of S1 after this edge. And then we can assign this state after this C-colored edge to the endpoint of this edge. And this will be consistent already with the new color. And if we also consider some node which is controlled by our adversary, then, and there are some C-colored edges that come out of this node, then adversary can go by all. In principle, he can use any of these C-colored edges. And then we just look, okay, what happens with the memory of S1 when any of the C-colored edges is played. And we just, then we, for all the endpoints of these edges, we can assign some state of S1 in a way which is consistent with the new color. And finally, an important moment that after this turn, after all these computations, well, some of the nodes actually, there might be more than one option to assign some state of S1 to them. But if you have more than one option, that's okay, you just choose any of the options that you have. But important is that, what's important is that your actual new current node should have at least one option. And this will be true because of the actual C-colored edge that was actually played in the game. We have been in the starting node of this edge, and we moved to the endpoint of this edge. And in our computations, we necessarily process this possibility. Okay. So that's basically it. I hope that this made sense to you, especially the last explanation, and I hope you liked it. So, and the link to the paper on the archive is in the description. So thank you.